Welcome to part 2 of the lecture. So you're really a brave lot to brave the weather and the fatigue from, 8 days of incessant talks. Just to remind you very quickly on what we did in the first lecture that was on Sunday before Mont Blanc. We sort of laid out the groundwork. We looked at the phase relationships in an OPA, and most importantly, we looked at the cases, how parametric amplification behaves dependent on different pump conditions, and particularly emphasized the problem of the pump duration. And you saw that we have one set of problems when the pump is very short in time because the pulses run through each other. And when we switched to quasi-static conditions in time, we took a longer pulse as a pump. And that's exactly the condition which is used in short pulse optical parametric amplifier. So as I mentioned, essentially we've done all the groundwork, and now it will be a lot easier to understand the remaining topics. So what we will do here, I will talk a little bit about the differences between laser amplification and parametric amplification, emphasizing the point when one or the other is most appropriate, so depending on the task. And to do that, I would offer some historic perspective, how things have developed, and from that you could sense where the problems are. So it will become very, very apparent that there are the so-called bottlenecks in technology. So that should be a relatively short segment of today's lecture. After that, I would like to switch to particular examples, what we're doing with such technologies in Vienna. And I will try defending a few statements that it's meaningful to go to the infrared in terms of developing high energy and few cycle driver laser technology based on OPAs, of course. Then I want to show very briefly one example of a technology that we currently can do only with OPAs. That is coherent Fourier synthesis of several components all at once, and that will be an example of the phase relationships that we looked at Sunday morning. And then finally, I will switch to Chi-3, and I will show you two examples of how nonlinear pulse compression can work so much better in the infrared. So that will be a complete segue back to where I started from by saying that when we try generating short pulses, we need to find a way either to maintain the bandwidth or to be able to broaden the pulse and compress it afterwards. So you will see that in the mid-IR, things are becoming much better because of intrinsically anomalous dispersion you're operating in. Okay, now this is the slide that we stopped on Sunday. I fell slightly short of the target, so the idea was to pass this slide and stop at OPCPA. But as a recap, it's very good. So it's just to remind you of the problem that if we take a laser amplifier, we need to ensure that we extract inversion from the amplifier with a high efficiency. To do that, we need to come with high photon fluence, so photon density per area. And if we don't stretch the pulse, that corresponds to a very high intensity, which would damage the crystal. So in fact, the problem of or the motivation behind short pulse amplification is not in the damage outright, but it's really the efficiency of the amplifier. You can make a very inefficient amplifier, and you wouldn't need to do short pulse amplification. And the tricks that we need to play is dispersion control. So we need to apply one side of chirp before amplification, and we need to G-chirp the pulse after amplification. So those are exactly the same building blocks that we will use in short pulse amplification, because we're also doing stretching and compression. But as I already mentioned, there's a different type of problem related to instantaneous interaction between the seed and the pump. So to ensure that the energy is flowing from the pump to the amplified seed, we need to do temporal overlap, and that can only be done by stretching the seed pulse, because the pump pulses that we take, they are intrinsically longer. Okay, so I'll show all the points here. This is the longest slide in terms of text on it. So I think it's very important to emphasize the differences. So the concepts, as you saw, are very similar, but in CPA, we're doing it in order to avoid the damage. Also, I didn't speak about that too much, but going through the amplifier material at high intensity, you're picking up nonlinear phase. And in some cases, this nonlinear case could be compensated for. It's the so-called whole beam self-focusing. So that could be filtered out and removed by spatial filtering. But if you go too high in the accumulation of nonlinear phase, then eventually that would lead you to the so-called small scale self-focusing, and the beam will either disintegrate, it will form hotspots. The hotspots will correspond to a much higher intensity still, so there will be an inevitable damage. It doesn't mean that the damage occurs on the entire beam cross-section at once, but it's enough to damage your optics somewhere in a tiny speck-sized area, and the whole thing is spoiled. So I explained the reason why we do it in OPCPA. So this is to provide time domain extraction. So there's also, of course, a concern about accumulation of nonlinearities, but since, as we saw, we can have a gain of 1 million in a single pass, this is much less of a concern. So for reference, in a typical laser amplifier, you're very happy if you have the gain factor of, say, about 2 or 3. For continuously pumped systems. For pulse pump systems, it can be significantly higher, but it's still orders of magnitude below what you can get from a parametric amplifier. Okay, so now, as I said, I'll offer a little bit of a history. And I already mentioned that the CPA technology and OPCPA technology, their bodies, they essentially appeared at the same time. And the first work on short pulse parametric amplification was done the year after CPA experiments were done, and that was published in the same year. So you already saw that image. It shows that the chirped seed pulse has produced a phase conjugated image, which is the idler pulse, and the idler pulse carried the opposite direction of the chirp. Then the first real OPCPA paper, which introduced the concept, was done in Vilnius. So I was very fortunate. I was still doing my undergraduate studies at that time, so I watched what my senior colleagues were doing at that time. So this is Audrius Dubietis, Gediminas Jonušauskas, who is now in Bordeaux in France. And of course, the idea belongs to Algis Piskarskas, so here on the left. So by now, Audrius wouldn't have dared to show his face like this, his head, but you know, age is causing some hair loss. So what this paper said, it gave a complete roadmap to how the area could develop. So they achieved really modest peak powers below 1 gigawatt, but they predicted, they prophesied that by employing existing nanosecond laser systems, you can go to terawatt powers and peak powers, and later people even constructed petawatt systems. And they took a 1 micron laser system, and to create the seed, they created a supercontinuum in the fiber and did this amplification. So since they had a stretched pulse, they had to compress it. So all the ingredients of short pulse parametric amplification were there. And so that marks the first paper. And after that, nothing in terms of OPCPA. But there was a lot of development in OPA in general, in femtosecond OPA. And this is important to understand why that was happening, because around 1993, virtually everybody who had little cash could buy a commercial titanium sapphire laser. So that gave microjoules, in some cases millijoules, in short femtoseconds. That's what Paul Corcoran was talking about, and it still remains the workhorse. And now they had a way of not only pumping the parametric amplifier, they also could seed it. So initially, the seed was done using superfluorescence. So this is a typical scheme where you come in with the pulse. So you divide the pump pulse into 2 arms. In the first passage through the crystal, you generate superfluorescence. Then you bounce it off back into the crystal, and you amplify it. So this is like an OPG technology that we talked about. And what was interesting, you could either attempt sending the entire available bandwidth of superfluorescence and amplify whatever is phase meshed by angular tuning of the crystal at that position, or you could try narrowing it spectrally with the diffraction grating and do narrow band, like 1 nanometer wide pulses, which are very popular in spectroscopy. So that was really an avalanche of different papers. All of them realized the merits of non-collinear phase matching. All of them used BBO crystal initially, and as I said, so that was the most important development, and sort of the OPCPA idea faded into obscurity for a while. So also very importantly, and I'm glad that Valentin is here, so I believe he was among the first ones who seriously explored the mid-infrared part and the crystals that were available at that time and still are the best crystals for this region. So that was also done using titanium sapphire as a pump laser. So this is not OPCPA, this is OPA, but different type of crystals. And OPAs, OPCPAs, they got the second boost in 1997, and as usually is the case, it came from multiple sides at the same time. It was a seminal paper by Ian Ross at the Rutherford Appleton Laboratory, and also the paper by Imra, where they used a fiber laser to build an OPCPA. So I'll tell you a few words about this seminal paper by Ian Ross, because he immediately came up with a proposal for a 10 petawatt laser, noticing the fact that people had lots of humongous neodymium glass lasers standing around. So those delivered only nanosecond pulses, but they had a lot of energy. So already in that proposal, they were talking about the possibility of doing 400 joules. And for this kind of ideas, still the best crystal is KDP or DKDP, and that's related to the size of the crystal that you can grow. For high energy applications, you would be frequently limited by the aperture of the crystal you can grow. For other nonlinear materials, as you have probably heard, it's kind of difficult to grow crystals in large sizes. So that was the trigger that created an avalanche, and the bandwagon started rolling of this OPCPA idea. So just to mention a few more things that happened on the way, we already talked about that the idea of using a coherent aperture, combining multiple beams to create a single pump source. So that idea, again, belongs to the group of Piskarskas. And the idea that I like very, very much for the beauty of its concept is the hybrid amplifier. It was proposed by Chris Barty. And here's how this idea works. So Chris also wanted to use the fact that people have big pulsed pump lasers for titanium sapphire systems. So those operated in the nanosecond regime. So it's easy to understand why. Those have to be Q-switch lasers. And the lifetime of titanium sapphire is like 3 to 4 microseconds. So nanosecond, the pulse duration is about the optimum to pump such systems with. But of course, they're far too long to be used for parametric amplification. So also, as we just saw from the argument, how far you need to stretch the pulse in the CPA, if you do it to very long nanoseconds, you have a problem because the size of your compressor would be huge. So actually, you don't need to go that far. Usually, people do it to a nanosecond or below a nanosecond, which again would be just a fraction of the available pulse duration. Now, where was the problem? If you continue with laser amplification starting from very low energies that you can get from the seed oscillator, your spectrum will narrow because of the gain narrowing. So it would be nice to have a preamplifier that offers a very wide gain bandwidth, and such an amplifier is a parametric amplifier. So to cut the long story short, what they proposed is to insert a preamplifier, which is a true OPCPA. So here is a stretched pulse from the titanium sapphire oscillator. As I said, it's stretched below a nanosecond. So this is 1/10 of the pulse duration of the pump laser. So the pump laser goes through. You amplify. So because of this fractional temporal overlap, you only create a small notch on the temporal profile of the pump laser. So after that, the remaining pump energy from the pump laser, from the green pump laser, goes into the titanium sapphire amplifier. And the titanium sapphire amplifier doesn't notice that there was a small depletion in the middle because it acts as an integrator. So that's really a beautiful idea that married almost the two conceptual enemies, OPCPA and CPA. And it has proven to be very useful because without the use of this broadband preamplifier, they got a narrow amplified bandwidth, and by building in this preamplifier, they broadened the bandwidth quite significantly. And nowadays, this kind of mixtures of OPCPA and CPA, they're used in many places. One of the biggest lasers that would be several times bigger than this room is the Texas petawatt laser by Todd Dittmeyer and the team. So you see that it contains parametric preamplifiers, and the rest of the amplification is done by laser amplifiers. Okay, so what became another small race is amplification around 2.1 micron. So you can guess why it happened, because people started exploiting 1 micron diode pumped lasers. And they wanted to make very short pulses. As we saw, the broadest bandwidth you can open is around the degeneracy. So that was the natural candidate to do it. So that was done in bulk crystals and piplins. So usually there was a bulk crystal as the last stage amplifier. And also people revived the approach that was pioneered by Valentin Petrov almost a decade prior to that, and they started looking very seriously at mid-IR crystals. And I will talk a little bit about that, showing that you can very easily build systems up to 4 microns. Okay, so this is like a summary of what I said in this very brief history. The main OPCPA developments, they were located in sweet spots. I already showed this graph last time without commenting on it much. So the position of the sweet spots is related to available materials and to available pump lasers. So nowadays, people tend to build high energy systems using the best available pump energy source. That would be either neodymium laser or terbium doped lasers, or the harmonics. The difference with tunable OPAs is that here we're looking for the optimal spot where we can open up the bandwidth, produce high energy, and of course get very short pulses. Now, in terms of the popularity, so as I told you, from the initial paper in 1992, there was nothing. There was vacuum. And then it grew steadily. And I think by now it has reached saturation. So the statistics for 2014 is not complete. I think we did the tally back in November. But people are growing somewhat lukewarm toward the technology because they have realized that it cannot really save the world. It's just one of many available techniques. But the progress has been very steady. Okay, now I want to talk about alternative ideas to temporal chirping. I think this is an excellent forum to sort of show ideas like this, because many of you here, they come from different backgrounds, and usually it's young people who can upset the dogmas. Since the beginning of short pulse amplification, people have been trying to come up with alternatives to it because they don't like dispersion control. And there are multiple approaches here. I will only talk about a few. So the big paradigms that I'm skipping, they're all related to coherent combining, interleaving, again, multiple beam combining, and so on. So I'm explicitly here focusing on the ideas of get around the problem of temporal stretching. So in many cases, this is very relevant because, for instance, for the pump lasers, we have a problem that the best media we have are not so easy to stretch because the bandwidth is narrow. But they would be excellent lasers also for pumping OPAs. And one idea that has many incarnations is that you multiplex the pulse, and after that you reassemble it from those constituent parts back together after amplifying it. So this incarnation relies on a series of birefringent crystals where you have different time delay for the passage of the ordinary and extraordinary waves. So that means every block in this birefringent sequence has to be twice as long as the block before, sort of to split the pulses and shift them and split and shift. And this operation is reversible. The other, so what you can do with that, you can really take, say, picosecond pulses, and without temporal stretching, you do pulse division instead. Another concept that I find extremely beautiful, and was hoping that Bob Boyd would be here because he was asking yesterday, but I don't see him. This is the tilted pulse amplification. It's only been demonstrated in a single paper, but it's a beautiful idea. It takes an initial pulse. So this is the black bar represents the energy flow. And initially, the direction of the energy flow and the normal to the wavefront are parallel to each other. But if you bounce it off a diffraction grating, then you get the so-called pulse front tilt. Now the pulse is tilted. Now, if you do a Fourier transform by means of a lens, you have the same effect which you have in GUI phase shift. So you pass the phase flip as you go through the focus. And that corresponds to rotating the image of the pulse. So you see that now, instead of going through the amplifier sideways, as it would be without this pulse tilting, you sort of lay it at the side. And the projection already corresponds to a long pulse. It has nothing to do with pulse chirping. It's simply the trickery with rotating the image of the pulse, but inside the amplifier, it appears as a long pulse. So I'm showing this for the beauty of the concept. It could be criticized into smithereens about how bad it is for amplification. And another idea is to use a spatially short pulse amplification, which is to have a spatial dispersion. So this is achieved here in a cavity by using two prisms. So the first prism creates angular dispersion. The second prism compensates the angular dispersion, but it leaves the spatial chirp. And that means that every frequency component now sees its own amplification spot. That was extremely popular about a decade ago in lasers. And then sort of the idea faded away until last year when Francois Legarret and Bruno Schmidt have applied it to parametric amplifiers. So Paul Corkum mentioned that a little bit. So the idea is the same, that you're going in with a short pulse, you disperse it, and now each frequency or each wave packet gets its own amplification crystal. So this is a mosaic OPA crystal. Each piece of the mosaic crystal is tuned to its phase-matched bandwidth. So I need to comment on the bottom panel here. So this is the seed pulse broadband continuum, and a number of crystals here are tuned to amplify individual bands here. After that, you do the reverse process. So you reassemble it back into a short pulse. So in fact, this is a spatial light modulator where instead of an attenuator in the Fourier plane, you implement an amplifier. So now, why is it so beautiful? This is beautiful because it solves many problems at the same time. And particularly, it gets around the problem of temporal stretching. Because the stretching is, in fact, done automatically. You separate the spectrum into individual wave packets. Each of them corresponds to a longer time already. Yeah? So then you can easily overlap them in time with picosecond pump beam. Also, since each of those quasi-wave packets is narrow band, it's easier to phase match them using longer crystals, and of course that could be done with a high efficiency. And dispersion compensation is also done automatically. So they call this Fourier plane OPA or FOPA. So I heard that it sounds like French faux pas, but I guess since it was invented by the French-speaking Canadians, they didn't mean anything bad with that. Okay, now this is the key moment that I want to talk about. So when is this OPCPA meaningful or competitive? Because I don't want to leave you with the impression that, using the cliche, that it's the technology of tomorrow and will always be. So now, we already talked a little bit about that we have extreme advantages like high gain and so and broad bandwidth and no heat deposition. We can also play tricks with dispersion control by noticing this phase conjugation. And of course, there are big challenges. And as a friend and technical director of Expla, one of the laser building companies, said, oh, OPA is a piece of cake. You just need to have the right laser for that. So I said it in the very beginning that the whole problem is whatever problem you solve in the OPA, you put it on the shoulders of the laser. And this is another comparison. I'll run through it very quickly. So indeed, the laser amplification, parametric amplification, they're similar, but there are nuances. Of course, we know that we're not dealing with real energy levels, and therefore we're flexible in our tuning. So we have different gain mechanism. So in one case, it's based on inversion storage. In an OPA, it's an instantaneous second-order nonlinear interaction. So if people tell you that there is no gain narrow in an OPCPA, don't believe them. I tried proving that in the movies, you show in the movies on Sunday by pointing out that when you stretch the pulse, then you have the one-to-one mapping of the spectrum to the time domain. That's the same idea that Maria referred to yesterday. So because of this quasi-linear chirp. So if you are leaving out some of that time window from the temporal window of amplification, that automatically leads to the loss of spectral components, which I understood is sometimes good for your applications. Okay, so the heat management. So for the laser, it all has to be done in the laser, so in the amplifier. So OPCPA is lazy, says the laser has to solve it. Now, in terms of spontaneous emission, that's actually getting on the quantum level, really. So potentially, we have a 4 pi solid angle for lasers. And as we, again, convincingly saw yesterday, we're dealing with phase matching immediately in an OPA. And therefore, we have a very directional flow of superfluorescence. Now, in terms of amplified spontaneous emission suppression, conceptually, the two techniques are very similar. You need to come in with a strong seed such that it can overwhelm the noise channel. So because the stronger guy will cause more stimulation and it will win out in terms of fighting for resources. And now the problem is that the saturation has a different origin. In a laser, you do by saturating inversion. Once you have depleted the inversion, there is nothing else to fight for. In an OPA, you're fighting for the pump energy, and the process is reversible, and therefore you cannot saturate to such a good level as you would do in the laser. So in a laser, potentially you can get the output stability which exceeds the input stability of the seed laser. In an OPA, never. Some people claim it, but I think there's very convincing evidence that it's not possible. Okay, and there's another interesting moment. That's actually what motivates a lot of people to go into OPA development is the attempt to improve the pulse contrast. So here, when we talk about pulse contrast, you need to talk about the intensity contrast, the energy contrast, which are different things. If you're interested, please ask me later. And in a laser amplifier, the best what you can do is to chop off the ASC, amplified spontaneous emission, by electro-optic modulators. So you just cut a window in time, and this window cannot be very short. So something like 200 picoseconds is possible. Whereas in a parametric amplifier, you can do it on a much cleaner, in a much cleaner way, and you can improve the picosecond background. Okay, so I said that the buildup of the nonlinear phase is not as dramatic in a parametric amplifier as it might be in a laser amplifier. But one should also take into account the fact that it's not only cell-phase modulation, or it's actually less of the cell-phase modulation, which is the source of nonlinear phase buildup, but it's more cross-phase modulation because we're mixing it with an intense pump. So something to remember. Okay, and now what are the bottlenecks of technology? This is a little bit of a controversy. We want to amplify the broadband spectrum, and we want to take an optimum laser for that, and such lasers are narrow band because they work better like that, and that means we need to find a way to synchronize the two systems. And all in all, it meant that the progress was very slow. So as an anecdote, the people who did it the first, they immediately refused to continue the work because they said that seeding with white light continuum from the fiber is rubbish, it's so troublesome, you lose the alignment all the time and things like that. That's because of free space coupling. That's sort of how annoying it can be. And as we already saw in the history slides, since about the middle of the last, no, that's already like, okay, since mid-90s, there was like a wildfire type of development of titanium sapphire-based OPAs for a very simple reason, because you could generate a white light continuum in a piece of material like sapphire, and you had both the seed, pump, synchronization source, all available at once. Okay. Now, I just want to show two examples where I think OPCPA is meaningful and when it doesn't make sense. So the question is, can it replace a short pulse amplifier? And the best CPA that we can have nowadays is still a titanium sapphire because of its huge bandwidth. So this is an example of a system at MPQ. Actually, it's its early stages. It has been upgraded and developed further many times, but that's where it really started making sense almost a decade now ago. And it provides a bandwidth larger than a CPA laser, pulses that are shorter than from a CPA, and it's very efficient because it uses a flash lamp pumped neodymium YAG laser. Unfortunately, this is a low repetition rate. Yeah? So this is like 10 hertz. I give to a system like that thumbs up because such pump lasers can be very efficient. So it is competitive against titanium sapphire. So the moment you go higher than 50 hertz, nowadays it's more like 100 hertz with that pumping, you start losing this advantage. Okay, so this is the low rep rate, high energy system that delivers hundreds of millijoules, and we are looking here only at the wavelengths of 800 nanometers. Okay, so now this is the opposite example. So most of the lab-sized CPA lasers, they would be something like a 1 kilohertz or several kilohertz in rep rate, and this is just a tally of resources that would go into building something like sub 30 femtosecond 800 nanometer amplifier using the laser technology and using an OPCPA technology. So here, as a pump source, we can live with Q-switch laser, which is very efficient, with direct frequency doubling inside the cavity. So it produces long pulses, long nanosecond pulses, and there's no danger to damage the pump laser. So the technology is typically neodymium YILF, in some cases neodymium YAG. In both cases, you can pump it with laser diodes. And in principle, you can just do it with a single laser head of the pump laser. Now, to do the same with an OPCPA, you would need all the same technology, but you need to get like a picosecond pulse. So you cannot do it in a single amplifier. You would need to have like 2 amplifiers, one to pre-amplify, one to post-amplify. So that already makes the price of the whole thing like triple as compared to the CPA arrangement. But there's more. Unfortunately, you require a much heavier pump in order to get appropriate gain. And you will be stressing your laser material so hard that you will be always walking on the edge of thermal fracture of the crystal. So you see that it's completely useless to compete with such a good technology as titanium sapphire when it comes to the same spectral range. And the basic conclusion is that OPCPA, fine, and it can exist, but it should not compete where lasers can do better. Okay, and now just to emphasize those 2 points about the pump laser and the seed. So the most promising laser is, of course, would be based on the terbium doped materials and diode pumped solid state technology or terbium doped fiber amplifiers. So even if you're not experts, you probably have heard a lot about the onslaught of diode pumped lasers, and it sounds like it's a relatively recent topic. So in fact, it is not, and it started back in 1964, and it's amazing. Seems like people who were doing it 50 or nearly 60 years ago, they were so far ahead of us in their thinking, so they knew it all. So they knew the correct materials, they knew the idea of cryogenic cooling, they used the same technology which we're perfecting ever since. So this is semiconductor diodes. Okay, and the technology has diversified itself in terms of the geometry. So one of the biggest problems for high power lasers is heat extraction. So you're trying to optimize geometry in such a way that you have a large surface area to extract your heat from. And compound problems are thermally induced birefringence. Also the buildup of this B integral. So for instance, we can take the fiber arrangement and it has a beautiful surface area, but then we would have an extremely long propagation length. And yesterday we heard 2 lectures about how fibers can be used to enhance nonlinear effects, and actually that's what you're trying to avoid for the good short pulse laser. Yeah? So it's exactly the opposite problem. So there are geometries like a fiber. A short fiber would be a rod that could be pumped from the front and the back or from the side. If you flatten it to create the surface, it could be a slab. And if you flatten it in the forward direction, that would be a thin disc laser or thin or active mirror laser or thin slab. So the problem here is with the thin disc lasers is that they provide very little gain in the axial direction, and therefore you need to go many, many times with the pump and with the beam that you're trying to amplify to bounce it off this material. Okay, so just to show you, without commenting too much, what causes extreme frustration in the design of bigger pump laser systems is the requirement to extract energy gradually, so you cannot do it all in one go. I refer to it as a sort of casket filled with water from which you need to take conversion out. So you need to come repeatedly with the same cup or the same bucket to deplete it. So that means that you need to realize a geometry in which you come into the crystal in multiple passes. That could be done in a cavity. So this is called, this approach is called regenerative amplification, shown here as a linear cavity and a ring cavity. So to be able to come in and come out with the beam after amplification, you need to have an electro-optic shutter. And when it comes to larger systems, particularly based on a thin disk, they can be almost 100 meters long. So very long cavities. Of course, they're packed, but it's a kind of whimsical technology no matter what. And that could be the first stage amplification, the so-called regenerative amplifier. The rest could be done in a multi-pass amplifier. Exactly the same problem. You need to travel through the material a number of times. So this is a proposal how to do it in a thin disk laser. So that's being done commercially for many systems now. That's another proposal which was pioneered by Institute of Laser Technology in Aachen. It's called InnoSlab concept, and now there's a big company, Amphos, selling many such systems. So the beauty of their approach is that they're fulfilling the requirement of coming in with the beam which is close to the saturation fluence. But after each pass through the amplifier, of course, the energy increases, so you need to stretch the beam in one direction to adapt to this condition of being close or above the saturation fluence. And therefore, they do this kind of zigzag of single passes, and the beam is shaped in one direction by using cylindrical optics. So continuing on the multipass idea, you can have different types of arrangements. You can have a sort of cavity-like arrangement using a confocal fold. The problem with the confocal fold is that the beam size in the focus is limited. If you want to build a high-energy system, you would need to dimension the system accordingly. So that has its immediate drawbacks. Then you can switch to a different type where instead of going in with the focus beam, you would go with the collimated beam, but then you need to watch out that the beam is re-imaged, and that introduces other difficulties like for re-imaging of the beam. So I'm not going into the details. I'm sort of trying to highlight the scope of problems. So to build a pump amplifier, you need to build a very, very good laser, and they're very complex. And as you can sense from that, they would be susceptible to mechanical instabilities. So people are associating a lot of hope with fiber systems. So fibers can be spliced together into monolithic chains, more or less. But there is an issue that because of the limited cross-section of the fiber, you can only store that much energy. It doesn't matter whether you're producing nanosecond pulses or picosecond pulses. And for single-mode fibers, it's on the order of single millijoules. If you go to large mode area fibers, you can increase that, but then you need to watch out what happens to the mode. A lot is being done on the fibers. So the main angle of attack at the moment is not to increase the mode of the fiber, but rather combine multiple fibers together and get a coherent output from that, either directly from the system of fibers or through other technique where you can store them in the cavity, the pulses. Okay, so this is just a glimpse of how big, complicated pump arrangements can look like. So this is courtesy of Franz Tavella back in the days when he was at Daisy, and it shows those slab lasers from Amphos and thin disk lasers for the post-amplifier stage. So that's the whole chain, and the chain starts with titanium sapphire laser. So you need to solve the problems, what goes into the seed arm, what goes into the pump arm, and so on. Okay, so another problem, as I pointed out, is how to synchronize the pump pulse and the seed pulse. If you're using long nanosecond pulses, that's kind of trivial because you can do it with simple electronics. So for instance, that's what you do in a titanium sapphire laser anyway. But if you go down with the pulse duration to shorter pulses, like picosecond pulses, you only have two choices. Either you need to do active stabilization, or you need to switch to a single front end. So let's say we've been through all of that over more than a decade now, and some attempts were done to start with two independent oscillators. So this is a titanium sapphire oscillator. This is a neodymium oscillator. And the cavity lengths of the two were actively stabilized. So that sort of worked with a sub-picosecond jitter. Could be done substantially better nowadays. So another way is to ditch one of the oscillators, keep the other one. And now you need to solve the problem, how do I extend the bandwidth of the 800 nanometer laser to have enough spectral brightness at 1 micron where the pump laser would work. So one idea is to use a frequency shifting fiber. So that's what Professor Loix was talking about yesterday. Use a solitonic pulse formation, and because it's done in a fused silica matrix in a solid core fiber, that causes a progressive redshift, and you obtain a bump in the spectrum that corresponds to the wavelengths of a 1 micron laser. So actually works remarkably well. And in terms of economy, it's a huge boon because you only need one single oscillator. And if you try very hard, you can also increase the bandwidth of titanium sapphire itself to go over 1 micron. So it's nothing revolutionary anymore. You can buy them for about 10 years now commercially. So to make the whole technology cheaper and not to be troubled by green pump lasers, you could also think about seeding it directly at the wavelengths of 1 micron. And that's what we've been doing for the past, 8 years. So you rely on the fact that the bandwidth of some ytterbium materials is quite wide. And it covers 1030 nanometers where broadband ytterbium materials are, and 1064 nanometers where neodymium YAG, the picosecond material, is. So essentially you can do the same, what you're doing here with titanium sapphire, but since the two wavelengths are so close together, this is a very modest oscillator, like no frills. And so speaking sort of from experience, we like such systems much better. So we stopped using titanium sapphire entirely. Okay, and now speaking about the parametric amplifier, I want to show concrete examples. So we are interested a lot in pushing the wavelengths to the red and toward the infrared. And that's because several lambda squared laws are involved here. So Paul Corkum has talked about that, the ponderomotive energy scaling, also the critical power of self-focusing scales is lambda squared. And when you talk about secondary sources like high harmonic generation, the cutoff of phase matching also scales quadratically. Could I just clarify one point? So my time slot is until 10:30 or until 10? Yikes. Okay, because I need to leave enough time for discussion. Okay, and the problem with, say, mainstream materials like BBO, BIBO, and others is that they don't really support the infrared part of the spectrum. So the best material that we can work with is KTA using the 1 micron pump. So you see the black bar denotes the degeneracy. So we deliberately tune it away from the degeneracy, and the idler goes toward the mid-IR, and the signal goes in the near IR. And that's another area that I hinted at, that we're also trying to extend it further into the mid-IR using a different type of materials, but that requires a new pump laser. So KTA is about the best crystal you can get in terms of its infrared transparency. If you look at atmospheric transparency, you notice that we're working within 2 transparency windows. One is around 3.5 microns, and it's limited on the long wavelength side by CO2 absorption at 4.2 microns. So this is like a good coincidence between what the crystal can support and where air absorption will start limit you anyway. On the blue side, it's 3.3 micron, where you're very sensitive to water absorption. And by a lucky coincidence, when you pump it at 1 micron, the signal wave goes into another transparency window around 1.5 micron. So actually, military people knew it for decades, and they were building nanosecond lasers. And it's because of the military effort that we have such great crystals as KTA, and partly the ZGP for further mid-infrared as well. So we can broaden the spectra and get continuum. Okay, so that's the idea of one of the systems, which is very representative. It shows how both OPA and OPCPA systems can be realized. So as I already mentioned, we start off from a single oscillator that synchronizes 2 arms, a picosecond pump laser and a femtosecond ytterbium laser. So then we use direct parametric amplification, so in the femtosecond range, amplified to the energy of somewhat around 100 microjoules. After that, we need to solve the OPCPA problem and stretch the pulse. This is the stretcher, which is applied to the near-infrared arm of 1.5 micron, and it has negative dispersion. Then we amplify it in cascades of KTA, and after that we compress it again using negative dispersion. This is because of the phase conjugation law that I talked about, only that in this case we're taking the infrared arm and not the 1.5 micron arm. Okay, and that's how systems look like. So the biggest component is the flash lamp pumped laser. And it can run at 20 hertz. If you strain it a little bit, you could build a similar system operating at 50 hertz, but that's basically where the technology would not pay off anymore. Right, and just to highlight 2 very interesting applications where this wavelength scaling sort of has proven itself useful. This is the generation of coherent X-rays that go all the way to the angstrom regime, so about 7 angstrom here at the cutoff. So that's what Paul Corkum has referred to. And this is the generation of incoherent X-rays from a sheet of metal. The advantage is very similar, so quadratic lambda scaling, and we can outperform the best results obtained with titanium sapphire lasers by orders of magnitude. So this is a collaboration with the group at GILA, And this was the collaboration with the group of Thomas Elsässer at MBI, and the work was done on the source in Vienna. Okay, so I promised one example on phase relationships, which we can only do in the OPA. And I chose it because this place is like Joseph Fourier University. So yeah, so let's see how we can dial in a waveform by using Fourier synthesis. And in an OPA, we have 3 waves. And we can choose the ratio of the optical frequencies and then can try stitching them together in a single waveform. So the purpose of doing that would be to modify the shape of the optical cycle. This is extremely popular in strong field interactions because, as you have learned from the lectures of Paul Corkum, you can, the electron feels the electric field and not the envelope, which is not a common situation for normal nonlinear optics. You would not be sensitive to the underlying structure of the electric field. So therefore, by playing with the shape of the electric field, we can do things like steering the electron the way we want. Now, the problem is how to get the phase relationships right. And you already heard one approach from Paul Corkum is that if we want to scale, for instance, high harmonic generation, we could either play with the laser intensity until we reach problems like we have pre-ionized the target even before we were able to apply the meaningful acceleration half cycle, or we can go to longer cycles. That's what we can do with an OPA. We can tune the optical frequency down, and that creates a longer oscillation cycle. And this oscillation cycle acts as a miniature accelerator. So you have a longer duration within which the electron is first accelerated in one direction, then stopped, turn around, and then accelerates backwards. So the longer the duration, the higher is the kinetic energy with which you can return. And that's the object of the exercise. And there's another way. So when we talk about this restriction, it's governed essentially by the so-called returning trajectories. So Paul Corkum has talked about that explicitly, that not every electron that you send out into the continuum could be used for harmonic generation, because you need to fulfill the requirement of a returning trajectory that returns it back to the core and allows it to recombine. So in fact, he was referring to that as Newtonian mechanics, and it's a very simple problem of equations of Newtonian equations of motion that gives you a number of so-called short trajectories, long trajectories that can lead to a meaningful result, and that gives you this pre-factor. So there is a way to change the shape of the optical cycle by doing Fourier synthesis. We can do it with an OPA again by displacing the frequencies of the signal and the idler. And that significantly changes the form of the waveform. And now different parts of this waveform fulfill different tasks. Like we have a high intensity peak that launches the electrons into the continuum. So we have more such electrons. And then we have a short fraction of the cycle that actually quickly accelerates the electron and pushes it back. So that idea was proposed by Luke Chipperfield in Imperial College London, and we've been working for a number of years on experimental realization of that. This is just one of possible examples where this thing is useful. For instance, it's also useful for the generation of terahertz, tunable terahertz radiation out of plasma. And I will not talk about that for the sake of clarity. Okay. Now, where's the problem? The problem is that we have pretty good ways of doing synthetic waveforms. This is, again, what Paul Corkum was talking about. You can combine the fundamental and the second harmonic or the third harmonic, and that provides you with the waveform where the cycle shape is fixed, although it can slide under the envelope. Yeah? So this, the carrier envelope phase is changing here, but the shape of the cycle under the envelope is steady. So you see that this interference bumps up every half cycle of the fundamental and sort of destroys every other half cycle. But they stay stitched together. Why? Because the carrier envelope phase of the second harmonic as a result of frequency doubling also doubles. So they intrinsically stay glued to each other. And now if we want to go for the so-called incommensurate frequency combination, say we want to take one of the waves to be 2/3 of the optical frequency of the other one, we can do it by means of OPA, and we'll probably derive them from the same broadened continuum, and they would carry the same carrier envelope phase. And therefore, if the carrier envelope phase is not fixed, then the shape, or the resultant shape, will change all the time. So I mentioned that in passing, but I didn't offer any proof of the statement in the last lecture, so I think by now everybody should be convinced. So to solve the problem, we would need to do phase stabilization, and it's not enough to have just, say, the signal wave and the pump wave intrinsically phase stabilized. So we can do it by deriving the seed through the process of white light generation, which is a 4-wave mixin, so chi3. But we also need to put an overall phase stability. So we need to start with a CEP laser. That would result in the signal and the pump, which are not only phase locked to each other, but they're locked to the CEP of the laser. So therefore, not only the relative, but also the CEP phase is locked. And the idler, as we have learned in such a system, is automatically CEP locked. So remember we discussed this relationship, and basically the point is that this really works. This is one of the experimental proofs where such an OPA was used, and by changing the shape of the optical cycle with 3 waves, we were able to fulfill just what we wanted, to have a very short acceleration lag, which quite a bit boosted the photon energy and the flux of the X-rays. Many more aspects as well, which I'm not emphasizing. Okay, and then the last segment, just in 4 slides. I want to talk about short pulse compression of long wave pulses. So as I promised, this is a sort of returning back to the initial point where I asked the question, what are the ways of getting a few cycle pulse? And one approach was to build an amplifier that can support the bandwidth. Another one was, okay, we're losing this bandwidth no matter what, and we want to restore it afterwards. And that's where we have to deal with the techniques of post compression. The technique, of course, existed for a long time, but the most significant development there was the invention of the hollow core gas-filled post compressor. So there was a capillary filled with noble gas, pioneered by Mauro Nisoli, Sandro De Silvestri, and Orazio Svelto. And of course, it would be extremely attractive to do it in a single step. So instead of broadening the spectrum and imposing some chirp on it, then later dealing with dispersion control, we would be happy if we could do it all in one go. And that will bring me back to the idea of using the conditions of solitonic pulse propagation to attempt doing that. And one of the problems is that we have techniques of external pulse compression relying on capillaries or filaments in gas. Have different nuances. Those work for millijoule energies, and provide sub-terawatt peak powers. We can also do a lot in the nanojoule range by using solid core photonic crystal fibers or even conventional fibers. For microjoule energy, we need to go for a large core diameter fibers, hollow fibers filled with gas. And I will show two realizations of this idea in the mid-IR region, one for microjoule pulses and fiber geometry, and another one for much higher energy pulses, tens of millijoules, and solid-state geometry. Okay, so the first thing is about those special fibers. Was also extensively mentioned in yesterday's laser by Gerd Loix. Our fibers, they come not from Erlangen, they come from France, from the group of Feta Benabit in University of Limoges. So the idea of this Kagome structure comes from the group of Philip Russell. So Feta Benabit was first a postdoc, then a senior researcher for a long time. So the word comes from Japanese, so it's basket eye, and those are Japanese baskets. I don't know if you can clearly see the structure here, this kind of cobweb structure. The point is that it has a very large diameter of the mode, so it supports a lot of energy, and there's virtually no field sitting in the fused silica structure, so it's almost entirely in gas, and that's why it's so important. And now we can differentiate two different regimes of external pulse compression. One is the traditional one relying on propagation and normal dispersion materials. So you have spectral broadening and a quasi-linear chirp. So this shows the evolution of the spectrum versus propagation distance normalized to dispersive length, LD. So you start from a narrow spectrum and then it broadens. And the pulse duration also broadens, but it has a compressible phase. So I'll quickly run a movie to illustrate that. Since the movie is quite fast, I need to explain first what you need to watch out for. So this is the spectrum in wavelengths. This is the initial spectrum, and you will see how it broadens. And this is the initial pulse duration. We'll take a pulse of about 80 femtoseconds, and you will see that the pulse broadens as well. And the red curves here and here, they will show respectively the group delay, which is the first derivative of the spectral phase, and the chirp, which is the first derivative of the temporal phase. Yeah. So, and you see that the spectrum begins to broaden and acquire characteristic bumps, and the pulse duration also grows. Yeah. And this still corresponds to a more or less compressible phase, so the movie runs twice. So that's how we broaden the spectrum, but we need the post-compressor for that. Okay, so if we're able to make use of the self-compensation conditions that were referred to in yesterday's lecture, so that the nonlinear phase caused by SPM is compensated by the linear phase of anomalous dispersion, we could sustain a short pulse. So unfortunately, I didn't see who asked this question yesterday. Is it possible to launch a pulse and have it compressed? The answer that Professor Loix gave is that if you're launching a solitonic pulse, it will stay a solitonic pulse. If you launch a pulse that is not solitonic yet but is capable of reaching solitonic conditions, it will form a soliton. It will stay there. So here we're talking about the condition where we're launching a pulse which is not a soliton yet. It propagates, and then we want to truncate the interaction at the point where it became the optimized soliton. So there's no sort of controversy in what you are saying and what I'm going to say. I'm just going to speak about the transient process as we form the soliton, and then we want to isolate it there. Okay, so the idea is like that the positive group velocity dispersion would be compensated by the anomalous dispersion of the material. And that's where the importance of the wavelengths comes in. So for wave-guided media, like this hollow core fiber filled with gas, we can detune the frequency of the OPA to be here in the strongly anomalous range. Now, remember that this is just the waveguide dispersion. There's no nonlinear medium in it yet. So we need to add gas. So to have it efficient, we need to add a lot of pressure, and the dispersion of gas stays normal. So therefore, by adding gas, the dispersion will creep back toward zero dispersion wavelengths. So the zero dispersion wavelengths will creep into the red. So that's why we need to start under the conditions where we're deeply in the anomalous dispersion, such that even by adding a lot of medium for nonlinear interactions, we're still in the anomalous range. So that's what we're doing in the Kagome fiber. And I will show another example where we can take our 4-micron OPA and simply go through bulk material, and we have the same kind of condition. So we have strong anomalous dispersion and optimum balance with the nonlinearities. Okay, just 2 slides. Okay, 3 slides. So that's how the evolution looks like when we have SPM plus anomalous dispersion. So the spectrum starts broadening. The pulse duration starts shrinking. So you see here we have achieved a single soliton. But if we don't terminate the interaction here, it will cause formation of multiple solitons or soliton splitting. So that's we need to watch out very carefully where to terminate the nonlinear interaction. It's also a very cool movie. I'm very tempted to show it again. You see that the spectrum broadens, the pulse narrows, passes the point where it was the shortest, and then it starts producing multiple solitons. So that's how the energy finds its way out. Okay, one more time, just to see. So the spectrum broadens. That was the minimum duration point. Okay, so how does it work in practice? So those are the 2 geometries, a piece of Kagome fiber with gas, as was discussed yesterday, or a high energy millijoule pulse going through a piece of bulk. For the first case, that's what we get out of a Kagome fiber at the wavelengths of 1.7 microns. So this is the initial spectrum, this is the broadened spectrum, and that's the initial pulse, that's the final pulse. So you can get even below a single optical cycle. Was published very recently. There's the paper that I promised to refer to. Essentially, we get energies something like 100 microjoules, and we have shown that they're good for generating harmonics, ATI, and such like. And the other case that I referred to for millijoule pulses, we're sending in something like 20 millijoule pulses on a piece of YAG, and we compress the pulse by a factor of 3, so it becomes like a 30 femtosecond pulse. And this is already close to a terawatt peak power. Now, where is the trick? So normally when you send such a pulse into a material, it will quickly split in multiple filaments, because here you're working at peak powers which are several orders of magnitude, almost 4 orders of magnitude are above the critical power of cell focusing. So if you don't check this interaction, it will cause what you see here in a long crystal splitting into multiple filaments. So it's the ratio of the strong anomalous dispersion in the mid-IR versus the still relatively strong nonlinearity that allows you to complete the process in a tiny fraction, something like 1 to 2 millimeters of the travel through the solid material, and therefore your spatial structure is not impaired yet. Okay, and that's the last thing I wanted to show from the experimental data. This is the pulse focus down in air without nonlinear self-compression, and this is with nonlinear self-compression, and this is already a true filament in the air, which is remarkable. So to achieve that at the wavelengths of 4 micron, you need to have a peak power something above 250 gigawatts, and we're at the level of like 700 gigawatts. Okay, so now the gist of the message here is that it's only possible for infrared pulses, and to get there you need an OPA. Okay, and that's the last slide. That's bad. Actually, it says here OPO should roll. And I put it up there because when I saw Zorro pods, the first association was it sounds like OPO, and of course, it's indestructible. So that's some of the recommended reading. Actually, it's a 3D painting, so if it looks fuzzy, it's that because you're not wearing 3D glasses. Okay, so I think I'd better remove that and go to this one. So thank you very much for your attention, and I'm very eager to get your questions.